Chordophones. Yeah, we have this survey, the Hornpostel sax classifications, ideophones that we had before, membranophones we had before, now chordophones, aerophones we had before, electrophones comes later. Harmonic relationship is general terminology. Harmonic relationship, a series of frequencies that are related through a common denominator FØ. Fn is n times FØ. If you say that FØ is the fundamental frequency. So harmonics in a harmonic relationship, F2 is 2 times F0, FØ, F3 is 3 times F0, Fn is n times FØ. The filter. A frequency, natural frequency, a frequency at which a system tends to oscillate in the absence of any driving or damping force. Mode. Maxima or minima in the function of impedance. The difference mode can have a harmonic relationship, like in the flute. Mode here, other modes, and there's a soprano phone, and there's a clipping here, a cutoff here later on. Yeah. Formant is different is from the mode of the vocal track named as F1, F2, F3. Each formant are mostly independent. So we have here loudness and frequencies here, 1000 Hz, 2000 Hz as a minimum, and so on. A as in father, A as in father. There's a figure here from sense of hearing, the Planck, and about this formants, the nasal cavity, soft palate, lips here, teeth, tongue, vocal folds, and larynx, strubehud, and here air from lungs, and the vocal folds opened, closed, open, and so on. And waveforms, time, pressure, F1 here, F2 here, and F3 here. So time and pressure, F1, F2, F3. The waveforms and spectra of two vowels with E here, and RCE and A here. The waveforms and spectra of two vowels, both with fundamental frequencies at 100 Hz. Okay. And showing the positions of the formants F1, F2, F3. Also illustrated in each case are the positions of the articulators in a cross-section of the vocal tract. A and E. Okay. And the definition, formant resonance in the vocal tract or the resulting peak in the spectrum of a speech sound. The source, the frequency component, a very narrow peak of energy at a specific frequency. The components here, 138 Hertz, 261, and so on, 880 Hertz. This is a frequency components. Narrow peak of energy at a specific frequency. Harmonic is a frequencies component are perfect or approximate a harmonic relationship. We will call each component as harmonic, numbered from 1 to n. And here remark, another convention is often used to numbering the harmonic from 0 to n-1. Fö, the common denominator of a perfect harmonic relationship, often we set F1 to Fö. So, okay, there are two. We can, this can be a little bit confusing. The fundamental frequency can be F1 or Fö. Here named F1, here F2, F3, F4, F5, F6, 7, 8. It's quite simple, and the amplitude here in decibels. Again, from a sense of hearing with Planck, waveform spectrum 200. The spectra is 200 Hertz, and then 400 Hertz, 600 Hertz, 800 Hertz. You can see it's harmonic. And if you combine those harmonics with 200 Hertz, 400, 600, 800 Hertz, you get a wave like this. And the spectrum here, over here, spectrum, here's the waveform to the left, spectrum to the right, 200, 400, 600, and 800. If you put 2, 3, and 4 together, here's 1, 2, 3, 4. 1, 2, 3, 4 gives this. If you put 2, 3, and 4 together, 2, 3, and 4, you get this. So we get a spectrum without 200 Hertz, but 400, 600, 800. An illustration of how a complex tone can be made by adding together pure tones of harmonic frequencies. The bottom panel shows the effect of removing the fundamental frequency of 200 Hertz. The chordophone. A definition. Any of a class of musical instruments in which a stretched vibrating string produces the initial sound. The chordophone definition. Any of a class of musical instruments in which a stretched vibrating string produces the initial sound. Part 1. The strings. We have here to the left acoustic of an open tube. Inversion of the phase of the pressure wave at the end of the tubes. Here inversions. Yes, pressure in with a plus, and then returns with a minus. Yes, and as we have seen it before, speed of the traveling wave is like this. C is the square root of this fraction in the denominator. Y is an adiabatic constant, is 1.54 for air, and P is an atmospheric pressure, about 101 kilopascal, 101,000 pascals. And we remember a pascal is 1 Newton per square meter, and rho is the air density. Pulse reflection from a fixed end. Here we have inversion of the traveling wave at the end of the string. See it here, boom, string, here here is the wave, comes to the wave to the end, to the wall, and then a version of the phase here when it returns back, reflects back. And yeah, we see here the speed of the traveling rate is the square root of the fraction tension in the denominator and mu per mass length in the denominator. We remember for the aerophones, end correction of resonant tubes is open. Yes, the pressure nodes in the end, in the two ends, where the pressure is 0. Here, let's go like this, pressure, and then it reflects back like this. And here you have the blue one is the physical length, and the L0 is the physical length, and L is the effective length, and we have the end corrections 0.3 times the diameter as we had before. Okay, same behavior. Acoustic of a string behaves as an open tube. There are some only differences in the terms of the speed. This term for open tubes and this term for string. First mode of a standing wave. I have like an open tube motion here, and the blue ones, and pressure here. The motion, the blue ones, are pressure, the red ones. The frequency is 1 divided by 2L times c, the speed of sound. This is this term 1 divided by 2L times square root of lambda times p divided by air density. And for a single stretch, strings attached at both ends. For a string attached at both ends, have L here again, and L here for the open tube. F is 1 for the string. The frequency is 1 divided by 2L times this square root, or you can you can make some changes in the term. 1 divided by L times D times the square root of T divided rho times P. It's because T is the tension in Newton, and mu is the mass per unit length. And mass per unit length is mass density times the area. So it's most times is rho, the mass density times the area is rho times p times diameter squared divided by 4. That's because those two terms are equal. String, acoustic of a string, all the modes. Fn is n times 2 divided by 2L times this square root, where n is 1, 2, 3, 4, and so on. L is the length, and T is the tension. Mu is the mass per length. And the natural frequencies, open tube, source with source white noise, not a clear percept, not a clear pitch percept, need to source to sharpen the tonality, and for fixed strings, source impulsion, clear pitch percept. And we continue afterwards.